consensus mechanisms really are the backbone of everything we do in crypto and every single crypto system and network that we make. It it all comes down to the consensus mechanism. So if you go to Google and you look up consensus mechanisms, one of the first things you'll see is some Investopedia article, which really shows you the peace of mind on where this fits into the investing landscape, because it really is where most the most value can really be created out of nothing versus maybe market positioning or a target sector. But when these projects that aren't necessarily companies work with consensus mechanisms, it opens up a lot of opportunities for some really innovative growth. And so just in general, the whole idea behind consensus mechanisms is agreement between nodes on the state of the network. And that's what you're going to hear everybody talk about. It's about agreement and it's about the state of the network, which is super specific, really hits in on a real specific topic. But in terms of what this looks like in actual reality, is you have a bunch of people that all come together and help form the ledger for a blockchain network. They help form basically the big list of everybody's account balances, that big triple entry book. And so there are very, very different ways that consensus, everyone achieves consensus on what my Bitcoin balance is, what everyone's account balances are. Here we have, for example, the Ethereum network, and it's pretty familiar, everyone kind of familiar with Ethereum, and you can see this graph shows sort of the distribution of people that mine Ethereum. Have we all just kind of in general heard of mining? All kind of familiar with what mining is? Okay, so yeah, you can see it distributed across the globe, and it's very, very decentralized, and you have thousands and thousands of miners in all these different parts of the world, and that creates a really tolerant network. If China comes out and bans mining, or if all the power goes out in Australia, it doesn't really affect the network, and at the end of the day, the entire blockchain system isn't just going to go down because a certain geographic falls apart, because you have everybody else in the network, and of course that gets rid of a lot of political risk because everything is really spread out across the world. Contrast that, for instance, with Ripple. Have you heard of Ripple? It's one of those older ones. Okay. It used to be really like the number 3 crypto on the planet. And here is Ripple's original validator list. You see you have about 21 validators, and if 10 of them go down, whoopsie, the entire Ripple network goes down. So you see some very stark differences between how these networks achieve consensus, and yet both of these were, tied for second and third place for the highest value crypto project for a very, very long time. And a bulk of why that is because of their unique consensus mechanism and then some of the cool infrastructure that they build on top of it. So here, for instance, is a mining rig. This is a mining rig I built when I was a kid. This is one that Abraham built. It exhausts into the dorm AC units. And these are basically, yeah, are running those being the validator, right? So this computer right here is an instance of just one of those nodes, and there are thousands and thousands and thousands of them. So it's kind of like you have this Amazon data center, but instead of being in one central location, it's really just thousands and thousands of just computers, right? These are all just standard computer parts. You could have a computer just like the one under this desk. You could have a laptop. You could have one just like sitting at your house, like a gaming computer, whatever it is. These are all just standard computer parts. It's like nothing special here. Um, you can get special hardware, but the idea really is that anybody can partake in the network and validate transactions for most of the schemes we're going to look at. And in instances like this is mining like Ethereum, so you can earn rewards based on that. Depends on how the network is structured. And what we're going to see later on, everyone kind of familiar with mining rewards, like Bitcoin mining, you get paid. What we'll see later on is a contrast between sort of networks that pay the miners, networks that have very so there's competition for the amount of space, and those fees get paid to miners, and we'll kind of contrast that with networks where fees maybe just disappear, they get burned, and how that really affects not only the value of a project, but also the sustainability of its networks, which is really cool. So in general, when we think about a database, for instance, here we have this Amazon warehouse, and say that this row of servers has all the logins and passwords for all the Google accounts, or whatever it is, and it's just in this one central location. Maybe there's like one backup of it by this one private company. But in general, if we have a ledger of, say, everybody's Bank of America account balances, it's all maintained by this one central party. And if one day the CEO of Bank of America says, hey, I don't like Alice, I'm going to get some money out of her account, for one reason or another, of course there's implications to all this, but the matter of fact is that really you can tamper with these central servers, and especially if they contain maybe private information, you know, there's just risks associated with that central data management. And we'll look a little bit more at the implications of centralization risks in just a minute. But before we do, I just want to contrast that to the way that data is stored on the blockchain, where it's literally just thousands and thousands of these these computers executing some software that keeps track of one big ledger. And so the really big key difference between these is that one little node on the network of thousands and thousands of nodes can't control what someone's account balance is. They can't just arbitrarily deny somebody from submitting a transaction because there are thousands and thousands of other computers that'll say, hey, I'll take that. That sounds cool. And that big difference is what most people have desired in computers for a very long time, because people fundamentally, you know, it's like probably not a good thing that if the power goes out or if lightning strikes here, we're not going to have anybody's account balances. If somebody, you know, blows up the buildings with all the account balances in it, um, and it destroys all the computers, like that's very, very bad. And so when you distribute these systems across the entire world, it really just creates extremely fault-tolerant systems. For instance, here we have Bitcoin. There are over 1 million Bitcoin miners mining everywhere across the road, 1 million nodes, putting in computers. You know, look at it a little more in a sec, and maybe you're familiar with it. But the idea is that it doesn't matter if 50 computers here go offline and 50 computers here go offline. It takes, give or take, 3 seconds for a general computer signal nowadays to travel across the entire world. So you can operate with servers that are anywhere on the planet as long as there's, at the end of the day, still one node running whatever the algorithm is. If it's like the Bitcoin script, as long as there's still one out of 1 million people on this network that's still running a Bitcoin node and keeping track of all the ledger history and keeping track of all the transactions, then the entire network, with some, you know, nuances, it still effectively functions, right? The data is still there. It's not like a lightning strike can just take out years and years and years of data, because for most of these systems, what you're going to see is that all of those individual computers, everyone that's participating in the network, has basically a full copy of the ledger, a full copy of all the transactions, and of course that creates a lot of fault tolerance. Now we're going to talk about the types of consensus mechanisms. And the first thing we want to separate are ledgers and kind of state machines. So these are more like Bitcoin has more of like a ledger scheme. Ethereum has more of a state machine scheme for some of the implementations of the programming on it. These are just big states of the network. It's a big triple entry bookkeeping ledger of everyone's account balances. It's that big list of everyone's information, versus what we'll see later on today are Dags and transaction sets. And these are more like, we have this transaction that links to this transaction, that links to this transaction, that links to this transaction. I remember from week 2, we all kind of heard of UTXOs. These are similar to UTXOs, but they provide a lot of really cool properties that we'll look at as we get into the consensus mechanisms. So in general, we're going to look at classical consensus. This is going to come down to cryptography that was established in the late 70s. We're going to look at proof of work. Oh, we're going to look at proof of, oh gosh. Classical consensus really has been around for a long time, but fundamentally, no one really made Bitcoin for 20, 30 and a half years, because there wasn't really a good way to achieve consensus amongst parties that don't trust each other, especially when you're dealing with money. If we have internet money and it's just a file on my computer, I can copy it, I can copy the file a bunch of times, I can just make a bunch of copies of it. And fundamentally, that was a really big challenge, because for a long time, because classical consensus only really works when you trust everyone. And we'll look at that in just a sec. And then we have proof of work. So Nakamoto, Satoshi came in and kind of really changed the game in 2008. And that's probably the one most people are familiar with. We're going to look at proof of stake, which isn't really its own consensus mechanism. It's kind of more of a classical consensus mechanism. So we're going to break that down. And that's kind of the second most popular one, if you know, kind of heard of it. These are the more popular ones. And then we're going to look at Avalanche, which is a newer consensus protocol that has some really cool implications. And the goal of everything we do here, the goal of all these consensus mechanisms, is just to make sure that this address, this wallet, this person, whoever this is, at the end of the day, has the right amount of whatever asset is on the chain, whatever asset is on the ledger, or however much money or assets that they own. And that's exactly what we're going to focus on. That's what all of these aim to achieve. Before we look at that, we're going to talk about the point of having consensus mechanisms in the first place and really where they fit into the whole crypto system space. So this here is Milton Kabera. He is from El Salvador, and before crypto came to his village and was widely accepted, he would every month when he wanted to pay his electric bill, he got on a bus for an hour. He went to a local town. He went to the bank. He sat there, waited about an hour for the transaction to process to pay his electric bill, and then he got on the bus for an hour again and came back home. And when crypto came into his village, that 3-hour process turned into 2 seconds on your phone, send off the transaction, bam, we're done. Where this fits into consensus is really critical. So this here is Carrie Lam. She's a big political guy, or political exec in Hong Kong. And when Trump passed some executive orders, what he did was bar Carrie Lam from opening any US dollar bank account. So banks would not open an account for Carrie Lam, similar to how a lot of financial institutions don't treat more impoverished citizens with the access to markets that they should have, because they're more impoverished, not going to generate as high fees. There's not as much of an incentive to service those individuals. Similarly, Carrie Lam here was completely cut off from the financial system, and she makes 600, 700 grand a year. So she would basically every couple of weeks have someone drive up to her house in a truck and just give her like a barrel of money, and she just hides it under her bed and puts it away in her house because she can't open up a bank account. Because she's been barred from the central authority, that central banking system. Similarly, the second challenge we're going to face is the idea of, say, we want to get this a helicopter car. I think it's really cool. You can buy this helicopter car with Bitcoin. It's about 6.5 Bitcoin nowadays. So aside from barring people from submitting transactions, what if we submit a transaction, I say, okay, cool, I paid for my helicopter car. I get in my helicopter car, I fly away, and then, the transaction gets canceled and I get my money back. And you're left without your helicopter car. That's a really big problem. And that's something that has happened multiple times on networks and blockchains that don't have up to par consensus mechanisms. Here are a couple of examples on the Ethereum Classic chain where you can basically max up the consensus mechanism, and in this case is you send $5.5 million, $6 million to an exchange, and then take out your money, and then you get rid of that send, and then bam, you keep your money, you also get all the money back. And the cost of attacks like that on poorly managed networks that don't have good consensus mechanisms are less than the potential profit. It's about half in this particular case. And so if you don't fundamentally design a solid consensus mechanism and have a plan to execute on it, you have networks that effectively, Ethereum Classic hasn't lost much value, and this has happened a bunch of times with them. But with a lot of networks, you'll have things like this happen, and the whole ecosystem just crashes. The coins go to zip. I've seen this happen a lot of times with very, very small projects. Someone comes in with a really powerful set of computers and just lies about the network transactions, and bam, the whole project goes to effectively nothing, and the guy pockets a couple hundred grand. It's a really big problem. So how do we solve all these problems? How do we make sure that everybody can submit transactions and we can't just arbitrarily block Alice? We can't arbitrarily block Carrie Lam. And of course, we get to our first mechanism, which is proof of work. So the idea, we all kind of heard of proof of work, kind of familiar with proof of work. I feel like this is the one most people know most about. We're going to look at this quick demo. Basically, the idea behind proof of work is it's pretty simple. You have effectively a computing lottery, and you just punch and crunch and crunch and crunch some numbers. So this is going to kind of act as our foundation for what a blockchain is. And then from this point forward, we're just going to talk about consensus mechanisms and not so much about data. So the whole idea is, say we have our first block here, and let's say Alice sends Bob 20 large, and let's say Charlie sends David $77, and we just have some arbitrary data that we're putting here in the blockchain. And in traditional chains and in networks, everybody agrees, okay, this is the syntax we're going to use for the transaction. Everyone agrees that this is sort of how everything's going to work out. And in general, you just come to just a collective system on how you want to execute your schematics. And so after you finish that, what it looks like in reality, So here we have our previous hash, and this is the first block, so there's no previous hash. And so basically, what this looks like in proof of work is we press this mine button, and what it's going to do is here we see this nonce up here, right? And that nonce is just some random number. And after we finish mining, what we're going to see is that nonce will change. It changed to 31,000 from about 11,000. And all that's going on while we do that is the computer just runs SHA-256 on basically all the data in the block, and you just want a certain amount of leading zeros, which is going to cause, it takes a very, very, very long time. So the idea that we learned with SHA and with public key cryptography is every single zero you add, it takes twice as many computations, basically in binary. So with base 58, it takes 58 as many times computations every single time. And so nowadays, Bitcoin blocks are like 19 zeros ahead of everything. And on average, it takes the entire Bitcoin network of 1 million plus nodes, give or take 10 minutes to kind of solve that transaction for somebody to pick some nonce that works. And again, remember, with this nonce, what we're doing is we're editing the data in the block, and any change in the data in the block will change the entire hash. You see that hash at the bottom, the whole hash will change with even the smallest change in the data. And that's why we just try arbitrary hashes, because every single block is different. And so since every single block is different, it has different data in it, we just have to keep trying a bunch of random hashes over and over until the computer has a certain number of zeros. And this might look simple as if you take a first look at it, but this really solved literally decades of challenges and effectively became a way to turn the work done by the computer into a provable work. So you could just randomly guess nonces, but the probability that you guess with 6 or 7 or 8 leading zeros is just trivial. It's extremely, very, very, very small. And so for someone to have a result that anybody can instantly check, anybody can plug in the nonce and say, and the given transactions, anyone can check and say, yes, this produces this many leading zeros. But to get to that point, every miner has to do tons and tons and tons of computational work, and that costs electricity, and electricity costs money. So what it did is it made it have an actual tangible physical cost to figuring out consensus, to executing mining. And contrast this to the decades prior Bitcoin, prior proof of work. Basically, everyone just trusted each other because they trusted each other in the real world. And there was no way for people that didn't trust each other to have some tangible way to form consensus and have a block that says, yes, this is the block. And Bitcoin and proof of work really came and created that ability for everyone to say, yes, this guy did a lot of work, he spent money, and there is some work, some math that has gone behind this. We can base our transaction on this block as long as all the cryptographic signatures are valid. And then in the next block, you just, same thing, you have all those transactions that are pending in the network. So say G sends to E, whatever, you have some transaction data here, and what it uses here is the previous hash of the last block. This is, I think, kind of most people are maybe familiar with this. You just use the hash from the last block in the next block, and then that's what creates kind of a linked list of all the blocks. That's effectively what the whole blockchain is. It's just a list of all these blocks. If we go ahead here and we mine block number 2, referencing block number 1 with the previous here, we can see it'll do the exact same thing. It'll go through about 10,000 of numbers and find some hash that has the previous value in it, the data in it, the nonce in it, the block in it. And you can see it takes the computer a while to do this. Excuse me. But it takes effectively, yeah, froze the computer. It takes the computer a while to do this, but it takes effectively like no time to verify everything. So in reality, when you implement kind of proof of work consensus, it's really simple to just say to everybody, hey, this is the nonce and this is my transaction set, and bam, confirm it, cool, we're going to go on to the next block. Yeah, so this has taken so much work. The computer is not even liking it. We'll give it a sec to go. Yeah, a lot. So you can see, it does all the computations. And basically the whole idea with how this is scaled over time is that people get more and more and more powerful computers, and that's kind of how it works. So it looks like this one is just a little bit much for Edge to handle. But in general, yeah, that's basically what it looks like, and you have confirmations, confirmations, confirmations down the chain. Cool. And yeah. In practice, with Bitcoin, for example, a lot of times you'll have miners come together and work on mining groups. And this is sort of the distribution of current mining pools where everyone comes together and works together. And see that there is some centralization of these mining pools, which is a concern and something to really think about. And it affects, because the people that control the mining pools can block transactions, they can try to do double spends. Generally, though, it's in the best interest of everybody. I mean, maybe you heard of this idea of best interest. It's in the best interest of these operators to act honestly because they get paid rewards in whatever the native token of the network is. They get paid their Bitcoin rewards, and they don't want to lose that. Solana is a pretty new infrastructure that's based on this same idea that it takes a pretty good amount of time to do SHA-256 hashes. It came out, give or take, half a decade ago, a little bit less than that. And since Bitcoin's been around for 15, coming on 20 years, give or take a decade and a half, there's been a lot of work on the SHA-256 hash, and it takes a very similar amount of time to do SHA-256 on very low-end computers and on very high-end computers on a single core. And basically the idea is that the ASICs and the ones that do this really, really, really quickly, they do it by running everything in parallel. And so the way that the Solana works is you initiate a loop every round, and in that loop you take some starting value that's formed through basically a collective consensus. It's usually just a random function that's generated every periodically, and you just do the hash of that value, then the hash of the next value, then the hash of the next value, the hash of the next value. And in general, hash 500 is going to take about the same amount of time for me to compute as it'll take Google to compute, starting at the same base hash. And once we get that 500th hash, everybody can confirm that it's the same just by really quickly looking at it. And you can confirm that I didn't do anything wrong, the miner didn't do anything wrong. And so Solana is creating this infrastructure where you can insert data into the hashes and associate it with the hashes and publish that to the chain, and then publish that to verifiers, and then publish that to that every block has sort of their own consensus round. And in Solana, the way that actually turns into reality, their current network statistics, at least what they claim, is give or take the order of 65,000 transactions a second with 800 millisecond finality, which is some pretty aggressive claims. And they're kind of making those based on this basis of the hashes taking time, and you can contribute them by using the hashes as a clock that everybody agrees to. Pretty valuable project. It's done really, really well, and it has a lot of really cool innovations. Next, we're going to look, so the idea behind most these consensus models is, say we have Abraham has like 10 of his computer things. Basically, the chain can split off, right? So when we computed those blocks, something maybe we've heard of, everyone kind of familiar with forks. I feel like it's kind of something that's popular. So you can have a fork here and a fork here, and remember that every block commits to the previous block. And so you just focus on the longest chain. That's how proof of work works. Everyone's pretty familiar with that. And so you just wait, generally like 6 blocks in Bitcoin, you just wait a while for the longest chain to be established. And the reason you do that is, say I'm an attacker and I can mine this block, then I can mine the next block, I can mine the next block, I can mine the next block, but not tell anybody about it. And then I can publish all of them at once and overtake the main chain. And in practice, with consensus mechanisms that have any sizable amount of computing power in the overall network, that effectively becomes computationally infeasible, or at least significantly more expensive than is feasible for anyone. And you also throw away all of those mining rewards. So in general, it's just extremely challenging, and basically it's like the same probability of SHA. Like once you get 15 blocks into the chain, you're not going to solve the challenge, right? So the idea is that it's a 1 in 800, what is it? Yeah, for at least for the current Bitcoin infrastructure, it's give or take 1 in 3 billion million chance that you will guess the SHA-256 hash just at random. And so to do that multiple times and not collect the reward for that is silly. And then also the idea that you're going to do that 6 times or so, you're going to have a 1 in billion, but it's not going to happen. For comparison, like the odds of winning the Powerball are 1 in 300 million. It's just trivially probably impossible to do. And so that's sort of the basis of chain consensus, and the basis of most modern blockchains will follow this same idea of probabilistic consensus. And when you're developing in this, it's a pretty simple kind of hash table to execute. And when you're investing in it, it's pretty well known and pretty established. Now we're going to look at classical consensus mechanisms. We're going to start with this basis of what we're trying to solve, and this was really most of the research that came out 40, 50 years ago. People wanted to form collective consensus.
How do you make absolutely sure that multiple entities which are separated by distance are in absolute full agreement before an action is taken? In other words, how can individual parties find a way to guarantee full consensus? Here's the example. Imagine that you are a general in the Byzantine army and you're planning to attack an enemy city. You have the city surrounded by several battalions, each of them camped several miles from the other, and each of them led by another general. A coordinated attack on the city from all sides at the same time will be successful, but an uncoordinated attack will likely end in defeat. You have decided to attack at dawn, but you have no walkie-talkies or cell phones, and signals from flags, torches, or smoke could be seen by the enemy. How do you make sure with absolute certainty that all of the other generals reach consensus and all attack together at dawn? You could send messengers on horseback, but what if one of them is captured or killed before delivering the message? You would need to have a reply from each of your generals confirming that they have received your message, which means that they would have to send messengers to you on horseback, but what if they are captured or killed? What if a messenger is captured by the enemy and an imposter messenger with a fake reply is sent back to you? And how do the other generals know that the messages that they received from you are genuine and haven't been intercepted and altered by the enemy? Worse yet, what if some of the other generals are traitors and they send messages back to you confirming that they will attack at dawn when their true intention is to retreat? How can you ever be absolutely certain that all of your battalions will reach consensus and attack simultaneously? Like I said, this problem has remained unsolved for thousands of years, and at its core, it's all about individual parties being able to trust each other directly, no strings attached. Bitcoin claims to have conquered this problem.
So nowadays, solving this challenge is actually pretty trivial using some of the basic cryptographic primitives that we have. So basically, you can just get a list of all the transactions that you want to include, and you have a base ledger that's just the starting point or wherever your initial point for the whole ledger is, and you say, these are all the transactions I want to execute on the base point that we have established, and then you just sign that, you cryptographically commit to it through a signature, and send it to the other validators in the network. And everybody then comes back with their signatures on that and just say, yes, I agree, I will commit to this and work with it, same as everybody else. And it's pretty trivial to get all that together and just execute signatures and then execute timeouts. And it's called Byzantine fault tolerance, and basically with most Byzantine fault consensus protocols, you can effectively tolerate about a third of the nodes just not responding because everybody else can come together and say, hey, we're going to agree, this is what we're doing. And then in modern crypto, it's pretty trivial to just send, okay, we're confirming this, we're confirming this. And in practice, as long as 2/3 of the nodes are honest, which isn't perfect, but it is what it is. As long as 2/3 of nodes are honest, or at least a third are not submitting fake double spends and stuff and blocking transactions, this is a pretty trivial consensus mechanism to implement. And this is basically what Hyperledger is. The way it works is in Hyperledger, you just specify what you want your nodes to be, and then bam, they just do this. It's pretty well established protocol. There's codecs for it. It's pretty simple. And it's pretty centralized because the question is, well, how do you figure out who these nodes are, right? How do you figure out who the validators are, who the peers are? So Hyperledger, you just basically arbitrarily pick, which isn't really that effective. Zilliqa is a project that if implements a similar, basically the same idea, but to become a validator, what you do is you do a proof of work. So you do a fairly difficult hash puzzle where you get a certain difficulty, do a certain amount of computing work, And after you do all that computing work, you get put into a round of the consensus mechanism, and then you become one of the validators. And the idea is that, it takes a lot of work to get into the group, and so a bunch of people that just want to halt the network or slow it down or not reply, it would take a lot of computing power to facilitate that attack, similar to how it would take a lot of computing power to branch off just the general Bitcoin tree fork on it. Cosmos is another project that's really big. They have a lot of really cool contract implementations on top of all this, and they combine this general protocol with proof of stake consensus every 50 or 100 so blocks. Um, and what you'll find, and basically you stake your coins or you stake whatever it is that you have that's of value. We'll talk a little more on that in a second because there are some challenges with that, especially when you're just starting out and whatever the crypto token is doesn't really have any value. How do you prove that you're staking something? It's kind of trivial. But with Cosmos, they have a really cool infrastructure, and it's based on this idea with proof of stake used to select who these validators are, just from the consensus protocol. And this proof of stake, this proof of work, and this arbitrary delegation of who these validators are is really important because this requires a lot of communication. And communication is one of the most expensive things you can do in any network. That's why when we looked at Solana, a lot of those hashing loops that we execute for an internal clock, they're done locally, right? They're not communicated with everybody because communication, like we said, to go across the whole world and back is give or take 2-3 seconds, and that's a fairly long time. And what you'll find with networks like these that are based on Byzantine fault tolerance is that the amount of time you wait for everybody to talk to each other grows pretty geometrically, and the cap on what you can really effectively have with these consensus groups is really about 100 validators. So anything over, give or take 100 validators, everything just starts to really, really, really slow down, and it effectively becomes unusable. So when you ever see any project implementing schemes like this, and there are a lot of projects that implement schemes like this that are very, very large. They're basically just classical consensus with modern cryptography and maybe a little spin on it with proof of stake. There are a lot of coins that literally just use this. What you'll generally find is they have a very limited number of validators. So we talked about EOS a couple weeks ago. It's like 20, or BMV is like 20 or 30 validators. It really puts a centralized control over the whole network, right? Instead of being thousands of peers, it's like 20 guys that just process all the incoming transactions. They're not doing all that mining. They're just verifying the signatures, but they can reject, if all 20 people in the group say we're going to reject Sally Mae's transactions, they can kind of collude and do that. And so in practice, these aren't really the most revolutionary schemes. There are a lot of projects that use them, but they have a lot of fundamental flaws at their core, and they're fairly challenging to scale. And yeah, so something we briefly covered here is this idea of a Sybil attack. Sybil attack just means, what if I make 100 validators, and I come and I act as 100 validators? I can just lie and take control of the network. Anyone here ever heard of Bing Rewards? Not so much? Okay. Basically, Bing Rewards is a program I kind of learned about in middle school. And every time you search on Bing, you get points, and you can redeem those points for like cash gift cards. So when I was in middle school, what I did is I made 10 Bing Rewards accounts, and every day you could go up to 25 cents in searches. So I would just search each of the accounts to the maximum, do like 200 searches on the accounts every single day instead of paying attention to my classes. And I make about 25 cents a day. And for me, I thought that was like, wow, this is cool. That same kind of attack is a really big problem in crypto, because if you can just arbitrarily enter the network as a participant, as a peer, a couple semesters ago, we had a project we did where you could take a survey, and if you got all the right responses, it was like a quiz, you would get like a gift card. And my partner who set up the survey part of everything made it so you could just generate arbitrary identities based off of emails. So you could just generate 20 emails, and then you could get like 20 $50 Amazon gift cards, and it cost them a lot of money. And so we want to set some baseline, some foundation of expense, right? So it's not just as simple as creating a bunch of email accounts to partake in the network. There really should be some expense or some contribution that you have to put in so that, some malicious guy can't just make a bunch of accounts and basically mess up all the consensus. Now, traditionally, the way this is done, this is Ripple. is you can just have one central entity say, okay, guys, these are all the validators. I checked out all these guys. These are all good people. I asked them if they would lie, and they told me no. So I trust them, and this is the list. Everybody has to use this list, and this is basically how Ripple works today. Is it's just using basically Byzantine fault tolerance, kind of a simplified, practical version of it, and just a big list of validators that's centrally controlled by Ripple. So if Ripple doesn't like people that have green eyes, they can never allow people with green eyes to be a validator, and they can have and they can kind of influence everybody else. And so that kind of central control is not great. Peercoin was one of the first systems that implemented proof of stake to try to move away from this idea that it should just be based off of one person. And so what they did when they launched is they were really the first proof of stake coin. The first, are we all kind of familiar with proof of stake? Like, so if you have $10 and Paul has 150 bucks, and everyone else has like 50 bucks or 20 bucks. It's just probabilistic, right? So it's just based on your stake, and basically every consensus round, just randomly you pick whoever it is based on their stake, and they have 50 seconds to submit their block of transactions and to claim the mining reward. Pretty basic stuff. Peercoin was one of the first to implement this, but when it launched, Peercoin wasn't worth anything, right? So you could have like 40% of the Peercoin supply, and it would be worth like trivially small amount of money. It was like nothing, right? So they combined it with proof of work consensus mechanism, where you had to actually do some computational work, do some script hashing, in combination with the two, and that was kind of the birth of proof of stake. Proof of stake nowadays is much larger. We've seen, for instance, this is the staking pool for the Ethereum. Everyone kind of heard of Ethereum 2.0, Ethereum going proof of work to proof of stake. Okay, pretty popular kind of thing. You'll see some of the same general centralization of staking pools that you see in mining pools. It looks trivially similar, and until you get to the other half of it. So it's actually kind of cool because you have a lot of really small people that stake, since you don't have to really, yeah. So there's a lot of nuances to that. But basically, you're doing this consensus based on the idea that Ethereum has value, which at its core is kind of a chicken and egg problem if you're trying to start your new system, because what makes something valuable. If you want your consensus mechanism to be based on value, it's challenging to execute at the beginning. So Algorand is kind of a newer token that came out, and they saw this and they had this new idea for a token, and they said, okay, well, we want to make this coin, but it's not valuable. So how do we do this? How do we do this staking? Because they didn't want kind of all the environmental impact from mining and proof of work consensus, and so they implemented this really cool kind of novel mechanism where they run a cryptographically verifiable random function every 20, 30 blocks or so. So they run this random function, and then that random function runs a lottery, and in the background, say you have, so it scales really, really well. So like we said, with normally when you have classical consensus mechanism, these are all kind of subsets of classical consensus. It really doesn't work well after 100 or so people, 100 or so peers. So with Algorand, what they did, they have thousands and thousands of validators. They're really well decentralized. And every time they run this lottery, every block cycle, they select like 100 or 200 accounts, and they select them in a way, or the code selects these accounts in a way that nobody knows who the validators are. So if you're trying to double spend or block somebody or do some malicious thing, you would have to know who all the validators are. And the way it works in Algorand is it just randomly picks some validator, and the only thing that validator can do is submit their transaction set, submit their view of the ledger, and move on to the next block. And as soon as they submit it, they submit that set of transactions that are pending alongside a proof that they were one of the selected accounts, which is just some arithmetic, some math. And as soon as they send it to the network, they only speak once, so they can't undo, they can't redact anything they say. And they are just a normal person now that they've submitted that to the network, and they propagate it to the network. And then, bam, they combine with all the other ones, and everyone basically decides to accept it or not accept it. And then that's kind of a pretty novel way to do it. It scales really, really well, but it still uses that same basic mechanism of only a few core validators. So we're going to look a little bit now at the Cell developers kind of broke away from Ripple, and said, hey, we want this to be more decentralized. We don't want to focus on just a couple of core peers. And so they used a principle of domain routing. So the idea is, say we're this computer here, and we want to connect to this blog website over here. In traditional internet routing, the way that works is you just find some arbitrary path that gets you to the blog. You try to find the shortest path, but you might be routed through a bunch of different providers to get to that blog. But as long as you just connect to some edge of the network, you connect to like the Georgia Tech IP servers, you connect to some edge of the network that connects to the larger network that connects to some other part of the network, you'll eventually find some path to get here. And this is basically the backbone of all internet protocols, the backbone of IPv. And the idea is that everyone, you ever heard of like 5, 6 degrees of separation? The idea that you kind of know everybody in the world, if by 5 or 6 friends, you can kind of find everybody. It's pretty similar to that. It's the idea of just a couple degrees of separation between you and basically every internet site, every internet hub, all the routers, all the domains are just a couple of steps away from you and the people that you know or the networks that you're on. So that's kind of the idea that Stellar took in, and they said, okay, well, we'll be this computer, and these will all just be arbitrary validators. And instead of, and basically the way it works is the validator, Alice picks, okay, I trust this guy, I trust this guy, I trust this guy. I know who these people are. They declare, okay, this is who I am. This is my website. On my website, I'm going to put this file that says I am who I am. This is my address. This is my public key. And basically, it's more of an organization-based approach where, this organization says, yes, this is me, this is who I am, this is my validator, and it's just based off of public reputation. And in practice, what that looks like is you just connect to the people that you trust, right? So you want to get to the blog, you want to maybe donate to the blog or whatever. You might trust kind of this organization, and Kivish, you might trust just like the Stellar Core, whatever it is. As long as basically all of these connections overlap, one way or another, all the peers in the network will share some path of connection. All the peers in the network will share the overlap, their loops of who they trust. And effectively what this looks like is every consensus round, you'll propose a transaction that you want. So say that Alice proposes this transaction and Bob proposes the yellow transaction. And say the yellow transaction is a double spend on the blue transaction, right? So they're going to different people. So every consensus round, what you'll have is thousands, you'll have all these transactions, and you send the transactions to whoever's in your validator list, and those transactions get sent to whoever's in their validator list. And basically all these peers say, okay, well, this transaction conflicts, right? So here, this peer has gotten both of these transactions, and he says, okay, well, which one did I get first? Okay, well, let's see. I got the orange one first, so I'm going to go with the orange one as valid, and I'm going to get rid of the other one. And then in the next communication step, real quick, he says, okay, well, I have both of these transactions, but it looks like my peers are agreeing on this orange one, and they'll just agree on what their peers agree with. And then at the end of the day, even though they submitted an alternate transaction, they're going to actually close that ledger eventually on the orange one. And that finality in Stellar is give or take 5 seconds for the block cycle. And the big idea behind Stellar is, say you're using some service by this guy right here. Basically, they would run some validator, and even though there might be maybe conflicting transactions across the network, as long as somebody settles down, right, as long as this guy settles on what you want, and then the whole network follows. Anyway, so that's kind of how you achieve consensus, and that happens every round. And what you'll notice here is I'm talking about transaction rounds and consensus rounds executing in seconds for some of these newer protocols versus minutes or hours to achieve finality in more legacy blockchains. And what you'll see is this has a really big impact on who these miners, who these validators are. So with the Bitcoin blockchain, it's the oldest blockchain in basically the whole world. And if you want a list of everyone's account balances, you want a list of all the transactions, you want to run basically the entire ledger, you want to download the full ledger, it's about 300 gigabytes, 400 gigabytes. And a lot of the a lot of there's a lot of the controversy what you see with all these protocols is, well, we should let more data be stored in the block so that there can be more transactions in the block. But at the end of the day, that leads to a higher requirement for all the miners, all the validators. So Stellar, for instance, has been around for give or take half, a little bit less than half the time that Bitcoin's been around. And the Stellar total ledger, total transactions, like everything, if you want to download everything, is over 1.2. It's like over a terabyte and a half almost. It's just a lot more data because you have a lot more transactions, you have a lot more blocks closing a lot faster, and so you're using effectively classical consensus with these overlapping careers. But with every consensus protocol, you really want to understand who is acting as a validator. In Stellar in particular is particularly unique in that basically transaction fees, they don't go to the validators. The validators don't actually make any money from just validating transactions on the network. All the fees get burned. And so it really affects that group of who comes in and acts as validator. And it also affects transaction fees. So Bitcoin fees, I think we've all kind of heard the horror stories of how much it costs to do some transactions, especially when the network's busy. Versus, on Stellar, it's fractions of a penny, hundredths of pennies for these transactions just by design of the protocol. And what you'll see is again, that leads to a higher expense on everybody else, on all the validators keeping up with the network. And so these are really important costs that lead to the growth of networks or the fall of networks, right? If everyone decides it's too expensive to validate, then everything's over, right? If nobody else is validating. Versus, if there's like one core validator that still has the whole ledger, then it's okay, it works, and we kind of agree with that. So those are really the biggest things to look at when you're investing in the projects. You really want to see where the incentives are for the miners and the peers, and just make sure there's longevity with that. And then when you're developing, effectively, you'll do a lot of work just looking at how some of these protocols are implemented already, and then having the knowledge of how everything works really lets you effectively merge whatever it is that you're inspired by into whatever the work is you want to do. Speaking of that, kind of what we're looking more at now are DAGs. So the idea with a DAG is instead of a chain where you have all the transactions in individual blocks, it's sort of more the UTXO model, but it's implemented without the block. So the idea is that you have some transaction, and then you can only go down some state tree, and you have accounts, and all these accounts have balances, and the balances are directly transferred through transactions, and kind of all the transactions are recorded, and they're all linked together. And that is kind of a fairly newer thing. There's not many protocols nowadays that are really implementing DAGs just as their own thing on their own. The idea behind it is really solid because effectively what you can do is if you want to submit a transaction to the network, you just validate two other transactions, and there are some projects that are trying to implement this, and that, with enough people transacting on the network, effectively turns consensus into an automatic process where you don't need miners, you don't need validators anymore, but instead it can just be contributors to the network. And this is kind of what we see is the future, and just a really cool way to sort of store that data and see it grow over time. And it's just not a whole lot on it right now, but it really has a lot of potential because it removes a lot of the external work that you need to do on consensus, and it bases it a lot more on the cryptography. And so that kind of gets us into our last consensus protocol, which is Avalanche. And Avalanche is designed really with DAGs in mind. And the idea is, say we have some node, and it learns about some transaction, and it asks all the other nodes, or it asks all the other peers, hey, do you prefer this transaction, or yes or no, right? And so what that looks like in practice is, say we have some state of the peers, and there is some transaction that gets executed on the network, and one transaction, I buy my flying helicopter car, and in the other transaction, I send the money back to myself. And so you'll have the helicopter guy, he's selling the car, he says, hey, what do you guys think about this transaction? Is this valid? Is this not valid? And what he'll do is he'll look at the colors, right? So just, it's like idealistic, right? So you have these colors that represent the state of a ledger or ledger branch or ledger tree or the DAG. They represent the state that this peer sees as material fact. And the way Avalanche works is really cool. It basically uses metastability. So everyone will ask everybody what they think, And then, so with this guy, he just looks at all the colors and just adopts so colors is kind of being used in place of the transactions and the history and the set, but just in place of all the data. And it'll say, okay, cool. Well, I have these two guys here that are blue, three guys that are blue, one guy that's green. I'm going to accept the blue state. And then everyone else kind of looks at each other. And you'll see here in the top, this guy has a blue state, but he sees three green states, so he flips over to the green state. And everyone that doesn't have an opinion will flip over to whatever it is that they see. And then over time, you'll see as these nodes contact each other. And this one here, it's just they see what they see, so they all communicate. And the communication here is just gossip protocol. So you just send out a bunch of messages and just locate peers. And you just adopt the state. So here, this guy sees three greens and one blue, and over and over and over, all you do is just adopt the state of the majority of the peers around you until eventually, through pretty probabilistic small amount of time, everyone gets to the same state. Everyone can append that to a DAG record, and then bam, you have consensus over the network. That's a really cool way to Avalanche. Avalanche is a crypto project. There is AVAX, and they're kind of the ones that pioneered Avalanche consensus. The way they implement it is alongside a proof of stake system. What you see with a lot of these projects, you have kind of two sorts of project developers. Off-Chain Labs is a pretty good example. They developed some really good layer 2 scaling solutions for Ethereum, and they don't have their own token, versus other layer 2 scaling solutions that do effectively the same thing. They'll issue some arbitrary token and say, this is the token for a protocol. And so that just so they can sell it to everybody and make a bunch of money at the same time. That's kind of what it seems like Avalanche, the AVAX, kind of the guys who developed this consensus mechanism have done with it. So every block, there's a consensus round in proof of stake, and everyone comes in, similar to how Cosmos works. Not the same. I'm glancing over a lot of stuff here, but basically, at the consensus level, without looking at all the other technical innovations, you'll see fairly similar. You have the staking, and that's used to figure out who these peers are. Notwithstanding, that said, this is really effective. So, everyone's kind of familiar with general throughput on most crypto systems. We talked about Solana at 65,000, but Bitcoin and kind of the other big ones everyone kind of knows are like fatefully slow. It's like a couple dozen maybe transactions a second. I think everyone's kind of heard this idea that Visa does a couple thousand transactions a second. If you look at the opening bell during 9:30 and at the stock market, you'll have sometimes like hundreds of thousands. Everything pours in really, really, really quickly. So a lot of times you need a lot of throughput, especially when you have like choke points, like everyone wants to start trading at 9:30. Avalanche is really cool because the consensus mechanism itself effectively scales with thousands and thousands and thousands of nodes. There's not really any challenge. Z- uh, Zilliqa also scales linearly because they use some kind of sharding magic. They're pretty good at linearly scaling. As more validators, they can have more shards of the chain, and they do some cool infrastructure on how contracts and how programming is implemented on the network. But in terms of raw consensus, Avalanche is really cool because it really gives you the most throughput with the most centralization without having to split up the network into different shards, without having to split up scaling solutions off of the blockchain. You're looking at thousands and thousands of transactions per second, like 16,000 or so transactions per second, with a theoretical upper limit of about 100,000 validators. 100,000, not validators, but just peers, kind of executing this consensus mechanism and kind of updating this DAG, acting as their own validators, acting as their own peers to keep everything in stake. This is what we're doing most of our work on with development. We really want to build a protocol that's based on this consensus mechanism, based on this DAG, that's not based off of staking some arbitrary token. And it really opens up a lot of really cool possibilities, not a scaling. When you get really deep down into crypto, like all anybody talks about is scaling, scaling, scaling. How do we get more transactions? Because a lot of times what you'll find is like Litecoin or Dogecoin, a lot of these crypto projects that people are very, very familiar with are, for those two examples, they're almost straight copies of what Bitcoin's done, because all the code's public. You can just copy it, and then bam, you have your own blockchain. Um, with a couple of tweaks, maybe a couple of modifiers here and there, but they're all very, very similar. And so just in summary, what we've covered today are the types of consensus mechanisms. We've looked at DAGs and transaction sets, which really allow a lot of that throughput with the idea of one-way transaction movement. And then we've looked at ledgers and state machines, which is more the traditional consensus route. And then we've talked about classical consensus, which has been around forever. And there are a couple of really cool, neat takes. Most of the revolutionary projects today are implementations of classical consensus with their own little twist on it. We talked about proof of work, which is really just the groundbreaker that really allowed all of crypto, that we know of today to come into existence and really gave a tangible base to all of the work that is done, to all of the numbers on that triple entry bookkeeping ledger that gave a real meaning and a real value to what was stated on there. Talked about proof of stake as a modification of classical consensus, and we briefly touched on Avalanche as a fairly new up and coming and really kind of revolutionary consensus mechanism that has a lot of really great potential. With that said, I'm going to hand it over to Paul, who is a core developer at Dash, and you said you had slides?
I sent you some.
You sent me some. Okay, I'll pull them up.
Okay, so one of the first things that I wanted to just kind of complain about is the Byzantine Generals Problem is definitely not solved. And so it's one of those things where practically we've been able to utilize it in a way that we've been able to create systems that are Byzantine fault tolerant. And they're able to handle nodes going offline, stuff like that. But the Byzantine Generals Problem is, in its essence, it's an impossible problem to solve. You cannot solve the Byzantine Generals Problem. You can just practically solve it so that it's probably fine. But the mathematical problem is still, it's basically unsolvable. One of the things that systems do, this is one thing that Ethereum 2 does, for example, the proof of service on Ethereum, is they will do slashing, where if you behave in a way that is objectively malicious, if you double sign, for example, you lose money. Your money just, poof, it's gone. It just disappears. You no longer have the right to move that money, basically. And that's really important because it disincentivizes you from doing these malicious things. Otherwise, you could double sign, you could do stuff like this, and your only hope is that enough people won't do it, but there's no problem with those people actually trying to do it. They can do it as many times as they want, they can double sign, they can act completely malicious, and there's nothing you can really do. Maybe you can remove them from being a validator, but you can't actually punish them. But with slashing, you can look at something that's objectively malicious, like a double sign, and anyone can see, okay, this private key signed two things where they should have only signed one. And you can say, okay, they're bad. We can take their money. So one thing with consensus algorithms is it's really important to be able to change them. And this is one thing that is very difficult in Bitcoin, for example. And there are really two types of changes. There are hard forks and there are soft forks. And I had a slide on this that actually, can I open it now? Maybe. So the gist is that a hard fork is something which loosens the rule set. It makes stuff possible that was impossible before. Whereas a soft fork makes something that was possible impossible. And so it's kind of two different ways to change consensus. It's really valuable to be able to do both at different times because a hard fork is inherently breaking. It will kick people off the network, basically. If someone's using an old version of the software, they will no longer be able to connect. And so Bitcoin has said, no, we're not doing any hard forks. Everything must be done in a soft fork compatible manner. That makes stuff pretty dirty sometimes. SegWit is an example of this, where the idea is totally fine. The implementation is iffy due to the fact that it is done in a soft fork compatible fashion. And it gets pretty technical to really explain why I think that's problematic, but the gist is that you have these old nodes that, in order to make SegWit soft fork compatible, they had to create these transactions in which old nodes think that anyone can spend them. The old nodes think that anyone can create a valid signature for this transaction, but the new nodes enforce some new rule that says, no, it has to follow this. So in practice, Bitcoin has done fine with it, but there are trade-offs, is the gist. Hard forks break consensus, and they kick people off the network, which Bitcoin has decided is non-desirable. But soft forks normally kind of create worse code. They make harder to maintain code. The protocol is a lot harder to understand, that kind of thing. So I want to look at the properties of a consensus algorithm. And so these are a lot of things that John talked about, but he didn't put names to them. And so I'm going to put names to them. Liveness, safety, permission, fault tolerance, and Sybil resistance. First one, liveness. This means that it will stay alive. If Bitcoin gets completely segmented, if the entire internet goes offline, people will keep mining. The protocol will keep going, but people will stop being able to learn about other people's progress within the protocol. But the miners will keep mining, and they'll keep generating blocks. And at some point, hopefully, the internet will come back on. And at that point, the network will collapse on the longest chain, the chain with the most work at that point. But during this whole time when no one was able to communicate with each other, the network keeps advancing, and transactions could still be processed. Safety is kind of what we talked about with probabilistic guarantees of like which chain is valid. Safety is kind of just that. It's safety about something being final. It's like finality. Bitcoin has no safety guarantees whatsoever, whereas it could theoretically come out that there is a chain of Bitcoin that deviates at like block 100 or block 2. It could go all the way back to the Genesis, and that's technically the longest chain now, and it's valid. And it would throw away all of the transactions effectively from the entirety of history. Pretty weird, but it could happen in Bitcoin, theoretically. Probably there would be a hard fork at that point because the value of Bitcoin would collapse and people would do things, but by the measure of the protocol, that could happen. And so there are alternatives, something normally like different models under proof of stake will give you guarantees basically that says, okay, if you see this message, you know it's final, and that falls under safety. Permissioned is very obvious. Is it permissioned or not? Can anyone access this system? Fault tolerance is basically the ability for people to fall off the network and the system to continue. Bitcoin is very fault tolerant, as everyone can fall off the network and it will keep continuing. And then Sybil resistance is the ability to stop people from just spinning up a bunch of nodes and dominating consensus. So I think John talked about Sybil resistance enough. So comparing consensus very quickly, proof of work, very high liveness. No matter what, it's gonna keep going. However, almost no safety guarantees. It's not permissioned at all, and it's very, very fault tolerant. Proof of stake is pretty different in a lot of ways, where it has medium liveness. If in most systems, it's going to depend on the system. In most systems, if 1/3 of the validators go offline, 1/3 plus 1 go offline, then the entire system stops. It halts. It's normally called a chain halt. And it's really problematic because your chain just stops and transactions stop processing and everyone thinks it's dead and you have to. Some chains will be able to recover from that, but normally if you have a chain halt, it's really bad and you kind of have to create a software patch to fix it and just force it to continue. Protocol normally isn't good at recovering from a chain halt. Proof of stake is arguably permissioned because you need the token to be involved in proof of stake. So you can't just start mining something. It's arguably permissioned. Nowadays, you could argue that proof of work is permissioned because you basically need an ASIC. For something like Ethereum proof of work, it's clearly not permissioned. Anyone with a GPU, which a lot of people have GPUs, can mine. So one of the things I want to talk about is how partitions are really dangerous without safety. So basically Bitcoin. China, Great Firewall of China, if they somehow are able to block all Bitcoin traffic, there will now be two competing chains. There will be the chain in China, and that will be a competing chain, and then there will be the chain in the rest of the world. Probably that won't be a problem because hopefully most of the hash power is in the global side, but what if it's not? What if most of the hash power is in China, and now everyone in the rest of the world is transacting on a chain that will probably at some point become invalidated. And there's no way to detect this in real time. You can kind of guess that, oh, blocks are taking longer than usual. Maybe something is going weird, but there's no way to know with certainty that there is any issue and that there's a partition. This is also can be really problematic because there can be attacks. And this becomes very problematic, and I think it would become very problematic in more more DAG-based systems and stuff like that, where if you are connected to a bunch of malicious peers, and if you don't have any good peers, they can feed you fake data, and they can make you think that you're on a different chain and different stuff. They can do a lot of attacks. Partitions are really dangerous, and it's very difficult to solve partitions. Practically, the way that Bitcoin works to solve it is by having a big list of peers, big list of seeds within the software that gets distributed, so that there are kind of all these fallbacks where if you can't connect to anyone, you try and connect to these seeds. It's very difficult to solve partitions, especially in like Bitcoin or different kind of systems like that. But it's really problematic in a lot of ways, and that's why you want to be careful generally, I guess, and you want more confirmations. But you can't know that there's a partition, so it's very difficult. So Dash's consensus mechanism is really interesting. It provides liveness via proof of work, so it will always continue. It will always keep churning on, but it provides safety via long-living masternode quorums, which are LLMQs, which basically derive their powers from the proof of work. And so it kind of solves this chicken and egg problem of like, oh, you have this proof of stake token, how do you start it? Well, the way that Dash did it is for years, it was a completely proof of work token. There was no staking or anything you could classify as staking. For some reason, a lot of the Dash community doesn't love the term proof of stake. In practice, that's kind of what we have, but we normally don't call it that. We normally just refer to long-living masternode quorums. And so in this system, but depending on what the quorum is doing, it'll either be 50 or 400 random nodes out of a set of 4,000, so 4 to 5,000. And so with this random set, you get really good guarantees, probabilistic guarantees that your set of 400 is going to be analogous to the total set of 5,000. And you're basically able to do proof of stake by asserting that stuff is final using these quorums. And so Dash has a lot of cool stuff. We have a dip defining this. But the kind of cool thing is that this proof of stake, if you want to call it that, is derived from this proof of work. And even if the safety guarantees stop, if the quorums stop working, the network will continue on using proof of work. But it's very obvious that, hey, something's probably going wrong somewhere because you no longer have finality, what we call chain locks. You no longer have chain locks. You no longer have that finality. But you still keep advancing. But you know, okay, something's weird. I want to be careful. I want to use a lot more confirmations than I normally would. You know, there might be a partition, something might be going weird, it's something to investigate, but you still keep going while also getting the safety guarantees. Where something like Ethereum 2, if there's a partition, if something weird happens, the network just halts, and that's not good. Okay, this becomes a lot quicker, I think. Oh yeah, I wanted to mention that this ledger and proof of history is not needed. All that matters is the current state and then future state transitions. If you can agree on the current state with the rest of the network, you're good. In a lot of ways, the decentralization of Bitcoin kind of flows from the fact that you can look at the entire history. But if you don't care about that, cool. Bitcoin is working on a thing called Assume UTXO, which basically just allows you to manually say, you know, this is a UTXO set at a certain block height with a certain hash, and I'm just going to assume that it's valid. I don't care about the history behind it. This is the tip that I care about. I think it's valid, and move on from there. Bitcoin currently, in different systems, currently kind of have this with what's called pruning, where you throw away the blockchain. You basically download it and you validate it, and then you throw it away because you don't want to use the storage on your local device. This is kind of a step further, where you just say, I don't even care about, you know, the fact that someone sent coins to someone else in 2011. I don't care. Just get rid of that. If those coins are still in the UTXO set, sure, because now I can validate transactions going into the future. But I don't care about the history. I assume the history is valid, and you can move from there. And this is really valuable from a like syncing time frame. Right now, Bitcoin takes like weeks to sync. You have to download 300 gigabytes to run Bitcoin Core. It's not great. And something like Assume UTXO is really valuable from that perspective. I think a lot of projects have something similar to this, kind of inherent in their protocol, where they have what's called like archival nodes that store the entire history, and then the rest of them just forget about it. And you can sync by just downloading the current state and stuff like that. You need to be careful because you do need a bit of previous state because there might be reorganizations or something like this. But as long as you have finality and you have safety, then you can use something like Assume UTXO. So the centralization of mining pools, we talked about this a little bit with your slide of kind of a, one pool has like 30%. This is actually really interesting, and it's actually encouraged by the protocol because of latency, network latency. There's actually attacks that mining pools will do where they will withhold their blocks for some period of time. They'll mine it, they'll have a valid block, but they'll start doing secret mining. They'll start mining on the side, and if someone else publishes a block, they'll now publish their block, and they hope that their block will be able to become the proper tip. But especially when there is a very high orphan rate. Orphan rate is basically the amount of forks that happen. When there's a very high orphan rate, mining pool centralization is really encouraged because bigger pools are less affected by orphan rates. Bitcoin has actually made a lot of progress. There's a couple of techniques called compact blocks, X-thin, graphene. There's a bunch of different technologies that basically make transferring a block really quick, especially to peers that already have a transaction set, already have the mempool. And that's really cool and uses some fun math, uses like Golem filters and some stuff. And so improvements like compact blocks have made this centralization substantially decreased, but it's still present in systems like Bitcoin. Merkle trees are really cool. They allow you to grab a transaction in log n time instead of having to download the entire block. This is how Bitcoin or Dash or any other blockchain-based cryptocurrency will work if you download it on your phone. And there are plenty of wallets that will do it. They might use a couple of different methods. There are different ways to do it nowadays. The earliest one was called SPV, Simple Payment Verification, I think. But basically, you use Merkle trees to get you use. It's complicated, but you use Merkle trees to prove that specific transactions are in a block, or you use Bloom filters to see which blocks that you care about, stuff like that. It's great because it allows you to use Bitcoin and different things on your phone and not take up much resources, but the security guarantees are lower generally. I want to talk about the speed of Bitcoin transactions. Bitcoin actually artificially slows down the rate of transaction broadcasting. So when you're running a Bitcoin node, you connect to normally 8 other peers that you send transactions with. And then they'll send it to their 8 peers and so on until everyone has it. In Bitcoin, they actually artificially slow this down as a privacy-preserving technique. Because if there's no artificial latency, there are some attacks that you can do on a network level. If you have a lot of nodes looking at the Bitcoin network and you're taking a lot of network logs, you can see, oh, this transaction started at this IP address. It's really problematic, especially when you see, oh, this person paid to Silk Road. Oh, and it was sent from this IP address. That's convenient. So you don't want that. In Bitcoin, it's really slow because of this. Dash is I didn't talk too much about Dash, but Dash has masternodes that are dedicated servers that are meant to do validation, and they're not meant to be like personal use servers. And so because of that, we don't have to make some of the assumptions that Bitcoin has to make about the fact that any node might be broadcasting transactions, because we can assume that if you're running a masternode, you're not broadcasting your own transactions over that masternode. And so our transaction propagation is like below 1 second to get it throughout the global network, and then we achieve finality within about 1.5 seconds. So it's really cool. But yeah, Bitcoin artificially slows it down, which is good, but also bad. And that's basically all I had here. So yeah, Byzantine fault tolerance and slashing. That's it. Nice and quick.